So we were just looking at a couple special series, but right now we're going to look ahead to the most common series, or the series we're going to be working with the most, which is called the geometric series. Now, before I get started, we're going to use this to do some huge help for us to take integrals of some difficult functions. Um, but that's a couple steps ahead. That's a couple sections in front of us. Right now, we're building the skill set to be able to integrate very difficult functions. But for now, we're just being introduced to something called the geometric series. And the geometric series is this. We start with n equals 0. A is some fixed constant. It's some constant. R is called our, it's our multiplier. And n is our variable. So it says find the values of s sub n through n equals 4, given that a equals 2. So we're just giving a value for right now. So, well, s sub 1 would be, well, let's start with 0 because n is 0. So s sub 0 is a, which is 2, times r to the 0th, and we know anything to the 0 is just 2. So that's our initial amount. So it's our constant. A is our constant. It's also our starting value. And s sub 1, well, that's going to be s sub 0 plus a sub 1. So that's going to be 2, that's s sub 0, plus a sub 1. Well, a sub 1, um, and notice this a is different from that a. It can get a little bit confusing. So what a sub 1 means our the term when n equals 1. So that's plus 2 times r to the 1. S sub 2 is going to be s sub 1 plus a sub 2. S sub 1 is 2 plus 2 times r to the 1 plus a sub 2. Well, a sub 2 is 2 times r to the 2. Notice that we could factor these a little bit. If we so chose, this would be 2 times 1 plus r to the 1. And this down here would be 2 times 1 plus r to the 1 plus r to the 2. Uh, so I think you could probably guess what S sub 3 is. S sub 3 equals S sub 2 plus A sub 3. Well, that equals 2 plus 2 times r to the 1 plus 2 times r to the 2. That's just S sub 2 there. That's this up here. Plus A sub 3. Well, A sub 3 is 2 times r to the 3. And again, we could factor this out. This would be factor out of 2. 2 times 1 plus r to the 1 plus r to the 2 plus r to the 3. So I think you could see that S sub 4 clearly would be 2 times 1 plus r to the 1, r to the 2, r to the 3 plus r to the 4. And geometric series is always going to work this way. We could replace 2, we could generalize this 2, and remember that this 2 is just our a value, the a value from right here. And that a value is our starting value. Um, all right, well, why are we doing this? We're working towards doing some integration. That's what we're working towards. But first thing we want to do is figure out what is the sum of an infinite. So infinite meaning let n approach infinity. What's the sum of an infinite geometric series following this formula that we just learned for geometric series a times r to the n, for n equals 0 to n equals infinity. So developed, well, actually, ooh, whoops, took this from the book, but I wanted to just talk you through how we can find an expression for the sum. So we take our s sub n, and that's just adding up all of the terms in the geometric sequence. So a plus a to the times r plus a r squared. That's exactly what we were doing before. Let me just go back a page. That's exactly what we were doing right here. Here's my a values, r to the 1, r to the 2. So we were doing that just a little bit ago. And what I'm going to do now is I'm going to multiply. So where I'm moving is trying to do some simplifying of this. But I'm going to multiply both sides by r. So I took this, multiplied by r, took this, multiplied by r, and then I get this statement down here. And the one thing that might look confusing is this last term, but we have a times r to the n times r, and r to the n times r is just r to the n plus 1. Adding the exponents, because this is like r to the 1, so n plus 1. And then what I'm going to do is think about, well, what would be the difference if I subtracted this top expression. So I'm going to take the top expression right here and do that expression minus this. So on the left-hand side, we have s of n minus r times s sub n. Getting this right here. And if we subtracted the right-hand side, the top minus the bottom, many terms are going to go away. So I have AR minus AR, those go away. AR squared minus AR squared, they go away. AR cubed minus AR cubed, they go away. And the only terms that are left over that don't subtract away is in the top I have this a value, and that shows up there. And in the bottom I have an a times r to the n plus 1, and we're subtracting, so that shows up there. How does that help us? Well, now we can get an expression for the sum of the nth term. And from this line to this line, it may not be totally clear, so let me just add in a step. What we did over here is we factored out an s sub n, and we got 1 minus r, just doing factoring. This is that, and that equals, a, factoring out an a, 1 minus r to the n plus 1, and then we just divided by 1 minus r. And this is that. So now we have an expression for the sum of the nth term. So in other words, as n gets huge, the sum of all those terms in the sequence can be found using this equation. This equation will find the sum of all the terms in the sequence as n gets huge if I know a and r. So therefore, we can say as n gets huge, as n gets entirely close to infinity, so in other words, the limit as n approaches infinity of this sum, so I'm figuring out what my sum approaches, equals the limit as n approaches infinity of, well, let's replace s sub n with what we found out that it equals, a times 1 minus r to the n plus 1 over 1 minus r. This is, as n gets close to infinity, this is what my infinite geometric series approaches. This is what the sum of the infinite geometric series approaches. It approaches this value here. So in other words, we know that the sum from n equals 0 to infinity of my geometric series, a times r to the n, equals the limit as n approaches infinity of a times 1 minus r to the n plus 1 over 1 minus r. And we're going to play around with this a lot right now and figure out, what exactly does this give us? What information does this help us see? So here's our sum of our geometric series. And the question is, what happens if the absolute value of r is greater than 1? Well, if the absolute value of r is greater than 1, then inside here, as n gets big, we're going to take, let's just, for simplicity's sake, let's say example r equals 2. So that's an example of when r is greater than 1. So this is just an example to help clarify this. If r equals a number greater than 1, for example 2, we'd have the limit as n approaches infinity of a times 1 minus 2 to the n plus 1 all over 1 minus 2. But what's going to happen, our denominator is fixed, but what's going to happen to this as n gets huge? 2 to some number, well, that's going to get hugely negative, but there's a negative down here, which is going to make the whole number positive. This, if we have some r value greater than 1 that's inside of here, it is going to be, it's going to make this whole expression get close to infinity as n gets close to infinity, because we're going to be raising some number greater than 1 to an infinite power, which is going to make that infinitely large. So this would equal infinity. Or, in other words, if r, absolute value of r, is greater than 1, we know that s sub n is going to diverge, because we'd be raising some number greater than 1 to an infinite power. So a number greater than 1 to an infinite power approaches infinity. Well, what if the absolute value of r is less than 1? And just for an example, let's use r equals negative 1/2. So I'm choosing a negative value, and the absolute value of that is less than 1. So the infinite sum, the sum from n equals 0 to infinity of a times, well, r is negative 1/2 to the n. If we plug that into this limit equation, that's going to equal the limit as n approaches infinity of a times 1 minus 1/2 to the n plus 1 all over 1 minus 1/2. Well, what's that going to do? Well, if we think about, it's the limit as n approaches infinity. The only place that we see n is in here. And as n gets huge, we're going to take some fraction. We have some fraction 1 over 2, negative 1 over 2, raised to a huge number. A fraction raised to a huge number, negative 1/2 raised to a huge number, is going to approach 0. So this would equal a times 1 minus 0 over 1 plus 1/2 is 3/2. So that's going to approach a finite number. So in other words, if our r value is less than 1, then s sub n is going to converge. So by looking at, in our geometric series, simply by looking at the r value, and remember, the r value of my geometric series is a times r to the n. If the r value is, the absolute value is greater than 1, my infinite series diverges. If the absolute value of r is less than 1, then my infinite series will converge. So I'm going to stop the video here. We're going to have another one.